invitation. Okay. Okay, all right, I'm in presentation mode and I've got my laser pointer. Okay. So, all right, thank you everybody for coming. I'll tell you about our new beamline at 9ID. And yeah, so this is my talk, but here are all my group mates in the dynamics and structure group. And the ones highlighted in blue are have especially contributed to the beamline and to what I'll be presenting in this talk. But while I'm acknowledging people, I should try to acknowledge more of the whole team, or at least briefly. And so Jin and Zhang here are the co-lead scientists for the 9ID CSSI beamline. I'm part of the science team, and Suresh is our group leader for dynamics and structure. Ray is our senior scientific associate, and he's been doing a lot of the installation and construction work. So I'll give a special shout out to him. But it takes a village to do work on this scale. So I won't name everybody. I'm sure I've unfortunately probably omitted people who deserve to be up here on this slide. But I am grateful for everyone's contributions and happy to be part of such a dynamic and impactful team. Okay, and then to just briefly describe, so I'll talk a little bit about the APS upgrade and then tell you about our CSSI beamline. The beamline is named for the new technique that we'll be hosting, Coherent Surface Scattering Imaging. So I'll tell you a little bit about that technique and the instrument just briefly, and then focus on the program in nanoscale structure, kinetics, and dynamics that we host that we also host at 9ID, and then the grazing-incidence X-ray scattering instrument, and the details of that, and also about and then I'll tell you about science highlights from the 8IDE user community, and in particular in these areas before I conclude. Okay, so I'm not sure if we've talked a lot about the upgrade in the context of this seminar series, so just a few words. So the APS upgrade has already rebuilt the storage ring of the APS now to support a multi-band achromat MBA lattice. So this is going to increase the coherent flux a few hundred times. And then as part of the project, there are 8 feature beamlines. And 2 of them, 8ID and 9ID, are in our dynamic and structure group within the X-ray science division. And then the kind of timeline. So you're right, Mark, we were saying before the talk. So it's in August of 2022 is when we decommissioned 8ID, which was formerly the home of 3 instruments. So 2 for XPCS in wide angle mode and in small angle geometry. And the 3rd instrument was for grazing-incidence scattering. So grazing-incidence scattering is on the 8IDE station and shared that station with wide angle XPCS. And now as part of the upgrade, the 2 XPCS instruments are staying at 8ID, which has been completely rebuilt. And the grazing incidence X-ray scattering program is moving to 9ID, which will also host this new technique, coherent surface scattering imaging. So in April 23, APS suspended operations. The storage ring was completely replaced, and then earlier in the spring, summer of last year was the progress towards becoming a working synchrotron again. 8ID has completed their shielding verification. They're starting to work with users again. And at 9ID, we had our first light around Thanksgiving time, and we've done some work towards shielding verification. It's in progress, and we're going to pick that up as soon as Beam becomes available again at the end of January. And so, so we'll be transitioning in this upcoming cycle into technical and scientific commissioning, and hopefully we'll get to work on some of our designated first experiments in this cycle. So let me tell you about Coherent Surface Scattering Imaging, CSSI, because it's not the focus of this talk, but if you understand a little bit about this technique, then I think it'll help understand the design of the new instrument. So CSSI is a technique that combines grazing-incidence scattering, so you have the reflection geometry like you see here, and it combines it with coherent X-ray diffractive imaging. So this is basically lensless, like you have lensless transmission, coherent imaging techniques. This is extending that so that we can look at 3D structures on surfaces or buried interfaces. Okay, and so if you think about this, this is really a lot like, I've already explained the geometry is the same as grazing-incidence scattering. So I use GI-XS a lot, grazing-incidence X-ray scattering, to denote both grazing-incidence small angle and grazing-incidence wide angle X-ray scattering, so GIXS, GIXS. So typically with GIXS data, you want to do, you get the 2D pattern, scattering pattern, and with some modeling, you can explain and get sort of an average description of everything that's in the footprint of the beam. With coherent surface scattering imaging, because you're relying on the coherent properties of the beam, we can apply iterative reconstruction algorithms so that we can invert the phase problem and basically recover from the scattering, scattered intensity, the absolute structure of whatever the mesoscopic, microscopic structure is on the surface or at buried interfaces. So at least initially, this is going to be developed with an eye towards applications in metrology for the semiconductor industry. So the goal is to look at complex structures created by modern lithographic methods and be able to reveal their structure in 3D. Okay, so that said, at least initially, it's maybe not going to be so much looking at soft interfaces. So so I'm not going to talk about it too much more. But you know, Zhang or Jin could certainly you should invite them back if you want to hear more about CSSI. I guess one more important detail of this technique is that the ability to invert the phase and apply these iterative reconstruction algorithms depends on oversampling the speckle pattern from the sample, and so you need to have you need to position your detector where the pixels will be actually smaller than the typical size of the speckle, and then so depending on the size of the beam, you can get pretty large oversampling ratios, but it does require fairly large sample detector distances and a detector with small pixels like the IGER-16M that you see here. And so that explains why, I hope explains why, or motivates why we have a very large flight path, which I'll show you in a minute. Okay, so now I'll transition to telling you about the beamline itself. So going upstream to downstream, I can tell you about our source. So here you see two of these revolver type undulators. At 9ID, we have one installed and space for another undulator, although the plan is for that not to be another revolver, but for that to be, I believe, a 21 millimeter period device. And here are the spectra and the coherence fraction. You can see there's a big increase in both the brilliance and the coherent fraction compared to what was achievable with APS. And this animation shows you the action of the revolver undulators, so we can swap between the 21 millimeter period and the 25 millimeter period, so that we can cover this full range from, so 9ID will be operating from 6 to 25 keV. Okay, and then this is kind of a schematic of the 9ID beamline, the way it looks now. And folks who are familiar with the old 9ID might recognize 9ID-A. That's the only hutch that's still standing from the previous beamline. Everything else was raised and now has been constructed anew. So the A station contains the initial optics, including the double crystal monochromator, which is with the horizontally deflecting double crystal monochromator. Then there's a mini hutch as our secondary optics enclosure, which has a CRL for transfocator for focusing capabilities. There's a second transfocator in the experimental station, where there's only one experimental station, 9IDD. And then additional focusing for the CSSI experiment, which benefits from a very small spot size, is from this KB mirror. And just downstream of that is a sample station for CSSI, which mounts the sample vertically so that the scattering plane is horizontal. And then I mentioned that we want to have a large sample detector distance so we could get good oversampling ratio. So kind of a unique feature of this beamline, we have a very large vacuum flight path that we've called the grand tube. So this external part is about 20 meters long. So we'll be able to get over 20 meters away from the sample at the CSSI sample area. And inside this tube, I'll show you later, is where our detector for CSSI is. Okay, and then the focus of this talk for grazing-incidence scattering, just downstream of the CSSI sample station in line is the grazing-incidence scattering sample station, and also an in-air detector for GI-XPCS. Okay, so I'll tell you more about that. Oh, and the same detector for CSSI is also our GIXS detector. Excuse me. Okay, what kind of performance do we get from this? So again, we're tunable over this range. And depending on what focusing elements we use, we have a spot size from about 30 microns down to sub-micron for the CSSI technique. Sub-micron is possible with the KB mirrors, and very healthy coherent flux. And then I guess just to note, the KB mirrors are always in the beam, but their focal length is too short. They won't be useful for the GIXS instrument, but they are in the beam. So they do. So for GIXS, the mirrors will be unbent. They'll be flat, but they will still provide a kick upwards and inboard of 5 millirad. And yeah, so here's looking at not just low energy, but low energy and high energy for the GIXS instrument. And the performance that we get from the undulator and the two transfocators. So again, we can have the beam of 30 microns or so down to a few microns in size, and the flux is higher at the lower energies, but still even at the higher energies, it's significantly better than what we used to be getting at the old 8IDE, where we were working at fixed energy of about 11 keV, and we didn't have too much by way of focusing. And then just an overview of the instrument. major principle is that we want to provide continuity of operations. So we're going to be basically migrating the heart of our instrument, so the diffractometer and this infrastructure, so our vacuum stage that supports GWAX and GSAX will be migrating to the new beamline, but we'll be expanding the Q range, and we still want to provide a variety of sample environments as before. So you'll see now with the new instrument, we have greater tunability, greater coherence and flux. We'll have more motion for both the GWAX and the GSAX detector, and we'll be capable of simultaneous GSAX GWAX, but that's pending a acquisition of a cutout detector. So on day one, we'll be having our Pilatus detector is also migrating from the old station. Yes, and so I'll tell you in more detail. So here you can see more close up what the sample station looks like. So just upstream is the CSSI, and then over here, there's a stationary granite piece where we envision that if users we can put some additional optics maybe, or have flexibility if users have larger sample chambers that they want to bring their own cells. Otherwise, our chamber is sitting here, and the wide angle detector immediately after, and then the entrance to the grand tube. And I'm not showing, but we'll have different transition flight paths available. So if we want, we can connect this. We can move the wax detector out of the way and move this, keep this all in a vacuum flight path with a minimal of windows, minimum of parasitic scattering. On this stationary granite, there are a couple blocks that are removable. So if somebody has a very tall setup, we can remove these blocks and put something else there. And then everything, the diffractometer is all very robust, and we can accommodate fairly large sample chambers or processing chambers. And so here's the sample environments that we plan to provide for users. So we already have actually installed now a hexapod that we've acquired that's just like the one they have at the new 8ID-I. And here it's shown together with a multi-cell thermal stage mounted on top. And that's actually the sample chamber we used for GI-XPCS on a previous experiment that I'll tell you about later. So we'll be able to do that here. And then we'll, like as I mentioned, we'll be bringing our multi-cell vacuum chamber along with us. We have an in-house developed spin coater that we can deploy at the beamline, as well as capabilities for solvent vapor annealing or thermal annealing. And then with users bringing additional hardware, we can work on operando experiments like electrochemistry or simulated solar illumination. With a source meter, we can both apply bias to samples and also measure, for example, photocurrent. And we're flexible and willing to work with users to mount other chambers. We have a collaboration with a scientist in the AMD division about doing some roll-to-roll processing at the beamline. So we're excited about that. We're also planning to deploy some efficiencies to optimize the beam time, since data acquisition should be faster, and we'll be sharing the beamline now with CSSI. So our overall beam time will be reduced some. So keeping things efficient will be good. So we're working on developing an interferometer system for alignment that should speed things up. And for routine kind of survey measurements, a robotic sample handler to make that faster as well. So then moving further downstream, we have our in-air GWAX detector. So we do have, so the detector will be mounted on a motion system. They'll be able to move it horizontally and out of the way, so that for the CSSI experiments, we need to put in a flight path that will create a vacuum path for CSSI. So that'll help reduce the changeover time between the two techniques. And on day one, we'll be using our area detector that's coming with us from 8IDE. But down the line, we would like to upgrade to a cutout detector, for example, this model from Lambda, or a similar model from Detectors that would allow us to pass the small angle signal into the grand tube and collect the wide angle signal simultaneously. And now I mentioned to you our grand tube. So here's an animation that shows you what's inside. So the carriage moves the full length of the detector, excuse me, the full length of the grand tube. So about 20 meters. The inner diameter is 2.75 meters, and that allows for about 1.5 meters stroke horizontally and about 600 millimeters vertically, which should make for interesting possibilities to optimize experiments. And oh, let me see if I can get back to, no, if I can get back to having a plain old cursor, then I could, oh, nope. Sorry, let me go out of presentation mode. Oh, and take you here. But I wanted to show you a video that'll give you a sense of the scale. So there's some PR from Argonne about our grand tube. So this, I think, gives you a better sense of the scale of the project. Yeah, it's a big guy. Oh, and as you can see, it's not contained within a hutch on the experimental floor. It's doubles as its own radiation enclosure. That also is something that limits the high end of the energy to 25 keV. So it arrived in four sections of 5 meters in length, and that was an early design decision. Was how big a section could we get through the truck lock and make the turn onto the experimental aisle. It was quite a project to be part of. The folks from AVS did a great job assembling it and working with Argonne survey and alignment to align it properly. And we're looking forward to putting it to use soon. Okay. So that's our bit of PR. Okay, and now back to here. Okay, and great. And then another animation. This is showing the motions for the detector. So, like I say, we have this horizontal and vertical stroke, and this is this size is necessary. Thinking about it for the spatial resolution that they'll be able to obtain with the CSSI technique. There's in the back. There's a second carriage with similar translations for a second detector. So we'll also have an pad detector that will have a higher instantaneous count rate. I think that will mostly be for CSSI. And then because we don't want to have to go in and out of this tube too often, we have a number of beam stops available. I think this animation is actually from an earlier concept. So for CSSI, with the sample mounted vertically and the horizontal scattering plane, we have to have horizontally oriented beam stops. So we only have, I believe, one layer, but 4 beam stops. Whereas for grazing incidence scattering, since the sample's mounted horizontally, and we have a vertical scattering plane, we'll have vertically oriented beam stops. I believe 3 of them, like you see here. We're sorry, there's only 2 here, but we'll actually have 3. Okay, and the detector, our workhorse detector is going to be this new IGER 16M detector. which is actually installed, I should say. I should have updated that. So you can see the specs here. The main thing, it's large format, about twice as large active area as our Pilatus that we used to use. Meanwhile, the pixels are less than half as small, only 75 microns. And the frame rate is faster, so up to over 500 frames per second. And yeah, we'll have it mounted on faster detection, and it'll be suitable for both GIXS and grazing incidence X-ray photon correlation spectroscopy. And we'll cover dynamics over a wide range of timescales. Yeah, and so this is kind of going to be the impact on the angular range. So compared to the image here is showing something typical for GIXS at 8 IDE, and we never did actually make our flight path large enough to cover the whole active area of the detector. So this circular outline is the cutoff from our vacuum flight path. And so that won't be an issue anymore with the new grand tube. And then also because we have more translations under the detector, instead of this symmetric view, which gets us plus or minus 0.25 inverse angstroms, we could either choose to have this symmetric view of about plus or minus 0.3 inverse angstroms, or we could move to one side and look at one quadrant, in which case our maximum Q will be extend to about 0.6, almost 0.65 at the same energy that we used to use. But with the tunable source now, we have a wide range of Q that we can achieve depending on what the experiment calls for. So different Qs and different resolutions. So you know, we'll have to start exploring that when beam is available. And then returning to the issue of oversampling, with XPCS, oversampling isn't strictly necessary, but we do want to kind of match the speckle size to the pixel size. And you can see here that that's achievable at much more modest sample detector distances. So for CSSI, the detector is probably going to spend most of its time at the far end of the flight path. But for XPCS, GI-XPCS, maybe it'll be somewhere towards the middle more, depending on the energy that we're using. Yeah, and then just a reminder about XPCS. You know, this is combining basically small angle scattering plus dynamic light scattering, and then in transmission mode. But we can also work in a reflection mode, grazing incidence mode, in which case it's like combining GIXS and XPCS. And the idea, right, we just have a series of images in the grazing incidence geometry, and then calculating the correlations between these different pixel by pixel between these different frames gives relaxation times like you see here. And then it's also good to note that spatial correlations between frames can be interpreted to give the strain that the sample is undergoing. And here's an example from transmission scattering, transmission SACS, transition small angle XPCS, showing how for a complex fluid, as you heat and cool the sample, there might be a kind of modest change in the overall scattering pattern observed incoherently. But with coherent illumination and following the XPCS data analysis, you can extract these relaxation times, and which clearly distinguish between the liquid state of the sample with a fast relaxation time and a gel where the relaxation time slowed down very much. So XPCS is very useful for characterizing the dynamics of samples, and we're happy that we'll be able to do that as well at the new 9ID. Okay, and so that's a lot of about the hardware, but software is also making improvement. So at 8ID has really been driving this for some time, and so before the upgrade, they were already making use of high performance computing where the detector was writing files to beamline storage, and that was then getting sent to clusters at the beamline via Globus for analysis. In the new scheme, this will be replaced at APS-U with the detector streaming data directly to large computing resources at the advanced computing facility on site at Argonne. And so we should be so users should be seeing almost real-time analysis, or at least analysis fast enough that they'll be able to make decisions about what to do next. Or potentially this could be tied in with machine learning AI tools to try to drive autonomous experimentation. And so we'll be borrowing that infrastructure for XPCS to handle GI-XPCS and 9ID, but we're also looking to upgrade our software for analysis of grazing-incidence scattering. So we've been relying for a long time on the very popular and successful GIXS GUI program written by my partner at the Beamline, Zhang Zhang, which has been hugely successful over the last decade or so. So it's a big shoes to fill, but we want to move away from MATLAB towards Python-based open source code. And we, with this team, we're working on moving forward to provide tools for users that can also be automated with and incorporated into the data management platform here at the APS. And we hope we can, generate, for instance, line cuts and pole figures on the fly. That'll be benefit users at the Beamline while they're still collecting data. And we're aiming for a rollout at the user meeting this year, and are planning for a workshop. It hasn't been confirmed yet by the program committee, but we hope to have a workshop so we can introduce this software to the user community. And now I'll be transitioning to tell you about some of the science, user science from 8IDE that kind of points towards the future at our new APS-U Beamline 9ID. And I guess I want to convey to you that we have had a vibrant user community engaged in a variety of areas. I'm going to focus on these three. So organic mixed ionic electronic conductors, OMIX, or mixed conductors, is a very active area now of research that's kind of grown out from the organic electronics community, which formerly was very interested in organic photovoltaics. And this is kind of one direction that research has grown into. So these materials form kind of a bridge from conventional electronics to biosystems, where silicon, for all its great performance, and we can design very high performance devices that transport electrons and holes, but that doesn't interface so well with biology, where things are kind of soft and squishy. And so you want things that could be wearable and implantable. That means they need to be stretchable, flexible. And OMIX kind of combine the best of these two worlds. And so because they are capable of carrying current both in the forms of electrons and in the forms of ions. So these are used to generate things like biosensors, like in this example from one of our users from Sahang Wang's group at UChicago, where they made this wearable patch that you could put on your wrist, and it had a neuromorphic circuit on it that could detect the wearer's heartbeat and also about the patterns within the heartbeat of whether the heartbeat is normal or exhibiting particular uh, known medical faults in the heart rhythm. And that's another aspect of this, because because these or this OMIX give rise to unique devices, one of which is the organic electrochemical transistor, in which the basically the gate material is formed by ohmiac material, and that means that um, the influx, the doping of that material by ions present in the aqueous medium affects the transconductance of that material. So basically, we have a transistor whose gain is controlled by the electrochemical state of the material forming the gate, or forming the channel, I should say, the channel between the source and the drain. And so that lends itself towards neuromorphic kind of computing, where you have, basically nodes, and the connections between the nodes can be tuned based on the electrochemical state of the device. And so that's how they can make something so functional out of really just not 9 devices in one patch. So that's kind of the upside of these, and we'll see how that develops further. But then other groups are using scattering techniques. This group does too, but I'll highlight some other research from a different group where they go more into the mechanism of these. So this is research in collaboration from Jonathan Rivney's group at Northwestern and Chris Takas at SLAC. And they developed a cone, they call it a cone cell, this nice cell that minimizes the aqueous volume of the aqueous medium over the thin film device. And so we can apply an electrochemical potential and also still do scattering. So in this case, GI-XPCS. And you can see from the line cuts, both in the in-plane and out-of-plane direction, that there are noticeable differences depending on the electrochemical state. They can also do similar things working with UV-vis absorption spectroscopy. And here you can see, zeroing in on this part of the scattering as a function of time. You can see how that changes with the applied potential, and here's how the despacing of that feature is changing with time, and how that tracks together with the UV vis absorption features that correlate to particular known electronic transitions in the material. So having demonstrated this kind of operando GI-XPCS and UV vis, then they also showed, so GIXS is also interesting. So working at larger length scales, you can see there's subtle but definite differences in the GIXS scattering, and it has to do with sort of flexing of these domains within the material, but also operando studies. So at 8IDI, we were able to look at this same material with XPCS, and interpret that XPCS data in terms of strain, as I mentioned earlier. So this orange curve is showing you the strain applied that the material undergoes as a result of the applied potential. And so so you can see actually that as the sample is polarized, it's causing a strain that compresses the material. And then as the hole is extracted from the volume and the cation migrates in, then the strain relaxes somewhat. So this is a very nice example of how we can bring all these different um, techniques together, operando GSEX, GWAX, and GI-XPCS. And right now, these required two different experimental runs at 8IDE and 8IDI. But now with APS-U and this new instrument, we'll be able to do these together on one instrument in one experimental run. So we think that's going to be very powerful. And then another active area of research in our user community is looking at perovskites for energy harvesting. I mentioned before photovoltaics being a big area. So perovskites have performance that rivals that of silicon, but not yet stability that matches silicon. So optimizing the crystal form is important. And the perovskites can be in sort of 3D crystals or 2D crystals like this, where there's a single layer of these octahedral groups. Or in between, you can have kind of a mixed 2D, 3D that with a different variety of layers in between. So this is n equals 2, n equals 3, n equals 4. So these are called mixed 2D, 3D, or sometimes just loosely 2D materials in between. And the important thing to note is the 3D material has the highest performance, but the lowest stability. And the 2D material has the worst performance, but the best stability. And so working with from Mercury Kinetics group and collaborating with Lin Chen, Justin, who was our user when he was a grad student and now is a Beamline staff at 11ID, was working on in operando. Oh, this movie won't start for me, or maybe it will. Great. So operando GWAX of spin coating deposition. So you can see in this case with the n equals 3, so three layers in the mixed structure, we get this well-ordered state. And you can actually see that as time goes on, the ordering is a little bit worse at the because the nucleation starts at the interface and then propagates down into the bulk. And when once all the solvent's removed, things become a little bit more disordered and the correlation lengths actually decrease. So and then they looked at this more systematically as a function of the layers, and were able to extract different mechanisms depending on the stoichiometry of the system. And right, and then also with the Kinetics group from Northwestern, but led by Aditya Mahita's group at Rice University, they took this to a very nice direction where with careful selection of solvent that dissolves the 2D material but not the 3D material, they could deposit a 3D layer for the photovoltaic, and then on top of that place a 2D perovskite layer as an encapsulation layer, and to protect the stability to passivate the device and get better stability. So here you can see that varying the incident angle, GWAX confirms the presence of these two different phases on the surface and then in the bulk of the thin film. And then the performance, you can see this black curve with the 3D bulk layer passivated with the 2D film on top. The performance, the power conversion efficiency of the solar cell is unchanged over more than 2,000 hours, so much better than the unpassivated film in blue. Okay, and then I think and then here's another area of organic electronics from Ying Yao's group at UIUC. And so they're looking at this particular molecule, which forms a variety of different polymorphs. And they found, looking at optically with polarized microscopy, they can see transitions, certain polymorphs transition in a cooperative way, where there's a very rapid transition, and others have follow more of a nucleation and growth formation that's much slower. And we can also see that with in situ GWAX with thermal annealing. You can see changes in the pattern that correspond to this shift in the unit cell. And so this could be the basis for new devices. For instance, since there's also here in this optical picture, you can see how for large single domain crystals, this change in the polymorph results in a macroscopic change in the length, overall length and shape. You could imagine, and indeed in this paper, they did demonstrate that they could form actuators based on these devices. So maybe other devices as well. And okay, and that brings me to the end. And I just so thank you for your attention. I hope I've shown you that we have world-leading instruments that we're developing at 9ID. So CSSI will be truly a unique instrument for imaging structures on surfaces and buried interfaces. We're very excited about that. And also the other half of the time will be spent on grazing-incidence, SAX, WAX, and XPCS. And so we're excited to be able to unite both studies of structures and dynamics on one instrument, and we hope that will lead to good synergies and new directions for research. So thank you very much. I appreciate everybody's attention, and I'm happy to answer questions you may have.
All right. Thanks, Joe.